All right. Good morning, everybody. So today we'll continue with optical properties. But before we do that, I'm just going to go over briefly the scores on the exam 2. Now that everyone's scores have come in. So the average is 76%. This is the distribution of the scores, as you see here. I should note that the average score and also the raw scores that you see here are just from the exam. So they don't include the 5 points that were allocated for the note sheet upload. And your TAs are going over those note sheets and they'll be grading them. And so if you haven't seen this reflection on Carmen grades, that is the reason why. And so by the end of this week, that should all be completed and you'll see the 5 out of 5 if you've uploaded a note sheet. And if you didn't upload a note sheet, then you would have marked that and that would also count as well. Okay, so that's just the distribution. And so just thought I share that so it's similar to exam 1. All right, so let's now continue on to optical properties. Okay. So this is where we were at when we dropped off last time talking about optical properties of metals. Oh, and actually one more note before we continue on to optical properties of metals. I wanted to also mention that, yes, we're fully cognizant of the fact that the pass, no pass deadline is coming up April 17th. And some of you have reached out to us asking about clarifications. We follow the College of Engineering guidelines in regards to the grade that would count as a pass or no pass. Obviously, this could affect your specific major in regards to do you need this course as one of the requirements or calculation into your GPA or admissions to the MSc major. So if you need to talk about that, obviously we can follow offline, but I would advise you to contact your undergraduate advisor because that person would have much better scope of, your major and also your portfolio. So that being said, feel free to reach out to us during office hours or via email. Okay, all right. Now we can continue to optical properties of metals. So where we left off was talking about metals and the fact that you can have absorption into multiple states. So from the filled states in the valence band, and then of course there's no band gap in metals, right? And so electrons can just be excited, with an incident photon, and as they relax down to lower energy states, the photon will be emitted from the metal surface. Okay. And so we were talking about, a relationship between metals and light that comes in with visible wavelength or infrared light. We also talked about ultraviolet, X-ray, and gamma rays and how they can actually be transparent. Metals can be transparent to these wavelengths because they're at a much higher energy. The wavelengths are much shorter. And so we talked about a concept called the plasma frequency, and that's the highest frequency light that can be reflected. And this is material specific. So what do we mean by that? So here are the wavelengths, right, in nanometers for different types of highlighted materials. So here it's 90 nanometers for aluminum, 139 for silver, 140 for gold. So this is the shortest wavelength that can be reflected. So what happens if a wavelength is shorter than this? Well, then your material becomes transparent, and those that photon can actually go through the material. So here you can think about having, you know, for silver plating, if you're trying to make a mirror, and if it's, if you have a wavelength that's coming in the visible, it's going to be reflected back because it's not transparent. It can't go through this silver material, so it gets reflected back, so you can make a mirror out of it, but in the visible. So if you have a wavelength that's, you know, ultraviolet X-ray, it can actually go through the material, and we use that for X-ray diffraction. And of course, if you think about ultraviolet rays, right, then that means if you have a really thin material, even metal, UV rays can actually penetrate through this material, and whether or not it will cause a sunburn, I don't know, but obviously the typical materials we deal with are, you know, not as thin, but once you get into the nano regime, you really have to consider the different optical properties of thin films and nanostructured materials, which of course is beyond this, slightly beyond the scope of this intro class. But for the most part, if it's a bulk type material, it's particularly metals, it'll be absorbed and then reflected back under this mechanism that you see here. And you can see that, right, that the reflection fraction, so IR versus I naught, is pretty high. So the amount of light that's reflected is actually quite high. So out of 1, it's 0.9 to 0.95. So that's where we left off, talking about optical properties of metals. We then went into refraction of materials and talking about the refractive index of ceramics and polymers. And when we talk about reflection, we talk about reflectivity, we talk about this ratio right here, IR divided by I naught being the incident intensity. And so if you, in terms of its relationship, reflectivity to that of the refractive index, so that tells us how much light is slowed down in your material. We have this relationship where the reflectivity is equal to the refractive index of, you know, if it's going into medium 2, the refractive index of medium 2 minus medium 1, refractive index of medium 1, divided by the N2 plus N1, and then that quantity, that ratio squared. So it also depends on the angle of the incident light, right? So if the light is not normal, there's some reflectivity, and or there can be also refraction. So there can be a combination where light will come out through the material, but at a different angle in which the incident light had come in. And if you're just going through air or vacuum, right, you can reduce that down to N1, the refractive index being normalized to just 1, right? So then your reflectivity, if you're going through air and then going through the medium, and then the light comes out refracted or reflected, that relationship is just simplified to taking into account N, which is now just the refractive index of that material that you're considering. So the example that's shown here is that for diamond, the refractive index, the index of refraction is 2.41. And so to calculate the reflectivity, you just take the difference between the index of refraction minus 1 divided by the index of refraction plus 1, and that ratio squared, and that'll give you the reflectivity fraction. Now, I talked about refraction and reflection. There's also a concept called total internal reflectance. So how do you get your light to completely just be reflected, right? Within the medium, there's going to be some angle at which if you come in through the material, there will be 100% reflection. Well, we can figure that out by taking into account Snell's law right here, where phi 1, so if you have your incident photon, it comes in at some angle, this phi 1, it can be refracted, right? So that it comes out at some other angle, phi 2. But there's some critical angle where beyond, so higher than this angle, this critical angle phi c, at that critical angle, you basically have no refraction, and it comes out, the light comes out at this angle. Now, if you increase that to this green dashed line right here, right, if that angle is higher, as phi 1 becomes larger and larger, you get reflection back, right? So you see here, it comes in, this is the end of your material, and it comes, it gets reflected back, and you can ensure that it comes back totally, so total internal reflectance once it's beyond this critical angle, right? And so this is obviously quite useful for applications such as optical fibers, which is of course how the internet runs these days. And instead of, you know, electronic pulses, you can have light pulses, and you can control that. Once you send in a light pulse, you can make sure that it goes out the other end, and it doesn't matter how wiggly your cable is, it doesn't matter, you know, the form factor of your cable. It ensures that the light that comes in will be totally reflected and comes out the other side of the cable. And so this is, of course, you know, quite revolutionary and is the basis of the internet as we speak. So let's do an example where we calculate the critical angle for diamond. So here we're asked, you know, what is the critical angle for light passing from diamond? So higher index of refraction into air. It doesn't work if it's the other way around for total internal reflectance, by the way. But here it's just asking what is the critical angle. So we can calculate that by knowing, okay, well, we're trying to solve for the critical angle. And we know that we want the incident light or the outgoing angle to be 90 degrees, right? So we want that, we know that beyond phi, when phi 1 is larger than the critical angle, then of course it will, you'll have total internal reflectance, but here at phi 2 at a minimum needs to be 90 degrees. So that means it's not being refracted. So then if we rearrange the equation from what we saw in Snell's law to, so that we can solve for what phi 1 is, or the critical angle is, and we know that phi 2, when we have phi 1 as the critical angle, phi 2 will be 90 degrees. And we know the index of refraction for both diamond and air. So we can solve that and replace it with the index of refraction for N2 is 1, index of refraction for diamond is 2.41. So now we take the arc cosine, or sorry, arc sine, and we get that the critical angle for diamond is 24.5 degrees. So of course, higher than this, we will get internal reflectance. So that's one way to manipulate Snell's law. Then we can also talk about how much light is absorbed as opposed to transmitted or reflected. So the amount of light that's absorbed in a material depends on how thick your material is and what is the absorption coefficient. And this will be different for different materials. And so here, that's given by Beer's law that tells you if you have some incident light intensity, this I naught prime, the amount of light that's transmitted, so reciprocal to that of the absorbed, I sub t is dependent on the beta, the absorption coefficient for that material, and the thickness of the material that it's going through, okay? And so when we rearrange and take the natural log of both sides of this Beer's law, we can solve for either the thickness of the material, or L, or beta, the absorption coefficient, right? And so when we talk about light intensity, we can talk about the power, right? So if you have some light, you can talk about the power, and so then any rate, the amount of light that comes back will just be a ratio. We can also talk about lumens, how bright, you know, one experiences that that light. But typically we want to normalize that. So when we talk about lasers, right, that's also, that's emitted light that we're trying to control in a coherent manner. And so there we talk about the power of, you know, in watts for that laser. Okay. So here, when we talk about optical properties of metals, specifically absorption, we briefly talked about it, where you can have here some filled states, right? And then there's going to be some unfilled states where you don't have a band gap. So going from here to here, you know, it's not a problem. You don't have some band gap to overcome. Now, if you want to get to higher states, then it will just go depending on the wavelength that comes in, right? Each wavelength has some energy associated with it, has some wavelength associated with it. That will dictate, you know, which energy state it will occupy, but it doesn't really matter because there's no band gap to overcome. So if you have some lower energy photon, then it will just jump to here, right? So because the electrons, the unfilled states are adjacent to the filled states. Now, let's say you have really high energy that comes in. Your photon is not just visible, right? It's X-ray. It has high energy, short wavelength. What happens then? You know, we've been talking about these valence electrons. You can also excite core electrons. So that's your 1s, your 2s orbitals, and that can happen. And so here you see an example from X-ray photoelectron spectroscopy, where if you have a sample, you know, let's say, you know, the blue rectangle is your sample, you can have aluminum X-rays. They're typically aluminum. This is the X-ray energy right here. So it's way higher than what we've been talking about in terms of the visible range, which is, you know, 1 to 3 eV. Here it's 1,486 electron volts. So that means it can excite your core electrons. And the way it does that is the impinging light will come in, excite a core electron, which will be ejected. That electron then will, you know, you'll have a range of electron energies that will come out. That all gets detected, and then you'll have a detector that then spreads out the energy again. These are supposed to be straight lines. And then that will tell you, okay, you know, did I have electron energies that correspond to, let's say, copper or iron or what have you? So you can do elemental analysis this way, and you can have an entire spectrum. Here you see the spectrum goes from 0 to 1400 for a copper sample. Clearly, if you have a multitude of elements, you can actually see which elements are in there, and you can do elemental analysis and backtrack, sort of reverse engineer the elements that are in your material. The other thing XPS is really good for is like surface analysis. So the impinging, the depth penetration for these X-rays going into your sample is actually 5 to 10 nanometers. So if you were wanting to know, you know, what's in my bulk, it's a little bit less useful. But if you start etching away the surface, you can do depth profiling, and that's particularly useful if you're trying to look at, you know, thin film samples for, let's say, photovoltaic applications. So it's quite useful. And so this is the photoelectric effect, where photons can come in, eject an electron, and then that gets detected. And of course, Einstein received the Nobel Prize for this in 1921. Okay. So it's been around for quite a while, well, the theory anyway. So how else do materials interact with light? Well, light can be scattered, and that's something we experience every day. For polymers, we talked about a little bit about how the structure of polymers will affect the optical properties, right? Whether or not the polymer will be transparent, or it will be translucent or opaque, right? So for highly amorphous polymers, we talked about that in the very beginning of the class, but just to review, so if it's pore-free and it's highly amorphous, there's going to be very little scattering, and these materials will be transparent, right? Sort of like your saran wrap, your plastic wrap. Semi-crystalline polymers. So here there are different indices of refraction for the amorphous and crystalline regions. So your material will scatter light differently. And so what you observe is that it will be translucent, and of course highly crystalline polymers will be opaque. So just knowing the optical properties of polymers will tell you something about the crystallinity in the polymer. And some examples that are listed here, you know, polystyrene. So we talked about styrofoam containers and why they're why they seem opaque versus clear and transparent. That's listed here, right? So amorphous polystyrene will be clear and transparent, but the styrofoam that you have, you know, for food containers, things like that, that has a lot of pores, and so it looks it looks opaque. Low density polyethylene, which are used in milk cartons, that say, you know, that's opaque when you buy, you know, that gallon of milk, it's opaque. But if you take a heat gun and you just heat an area of the milk carton, what you see is actually it'll start to get transparent once you make that, once you melt it and make it amorphous again, right before, of course, you blow a hole through your milk carton because you will have heated it through. Okay, let me pause here for a moment and check the chat section and see what kind of questions we have. Are these electrons flying off into space or just core to valence shells? Yeah, they're just being ionized. So Tony writes, yep, XPS, they leave the material and actually are physically detected by the measurement, correct. So the clarification, it's not they're just being excited to valence, although that could happen. And if a core electron gets excited to a higher energy state but does not get ejected or ionized, then what will happen is once it goes to a higher energy state, when it comes back down, we can have what's called Auger, A-U-G-E-R, Auger electrons, and we can detect that secondary relaxation. And there's Auger spectroscopy where people study that as well. The XPS method that I was talking about detects core to basically ionization, but you can also detect Auger in XPS as well. So those are different peaks, and they're typically noted as things as like KLL. So that means it goes from K to L. So S, you know, excited up and then relaxed down. So yes, there are multiple methods of relaxation for these electrons. Okay. So metals, polymers, semiconductors. When we talk about semiconductors, clearly we've been talking about them for a while, since crystal structure of material. And there we talked about, you know, germanium, we talked about silicon, and it's obviously particularly useful in photovoltaic applications where you have solar cells, and that's been used for a while. And amorphous silicon has been known for a long time, since the 70s, in regards to how more efficient it can make your homojunction photovoltaic cell. And so here, the absorption of light frequency, nu, by the electron transition can only occur if the incident photon has an energy, h nu, that's larger than the band gap, right? We talked about semiconductors having different band gaps. And so insulators have really large band gaps, metals have 0 band gap, and semiconductors have something in between. And so if your photon energy if its energy is larger than that of the band gap of your material, then the electron will be excited from the filled states, the valence band, and it will be excited to the conduction band. Okay. And so here you see a distribution of solar energy radiation. And this is taken from Lawrence Berkeley National Lab. And you can see here that in the visible region, less than half of the solar radiation is in the visible region. We can see visible, no problem, but if you have a photovoltaic cell, and what you really want is to maximize all these, the absorption, right? And so here we see that 6% of solar radiation is in the UV, a little less than half is in the visible, and then the other half is in the near IR. So that's 700 to 2500 nanometers. Okay. And so here, let's say you have a semiconductor, silicon, gallium arsenide. So that's compound semiconductor. So if your band gap is less than 1.8 eV, basically all light is going to be absorbed. If your band gap is larger than 3.1 eV, then for the visible region, it's really difficult to absorb that, right? So for violet, let's see, if we're talking about violet here being the shortest wavelength, red being the longest wavelength, violet is about 400 EV, or 400 nanometers or so, and about 3.1 EV, whereas red is more 1.65 EV. Right. So if your band gap is 3 EV, then the visible light that you have available, well, that's difficult, right? And then you're going into the UV region, and so the material will be it looks transparent and colorless. And then if the band gap of the material is somewhere in between 1.8 EV and 3.1 EV, where now you're going into the ultraviolet region, there's going to be some partial absorption. So any sort of wave, a photon that comes in the visible, it can be absorbed, in some fraction. And what that band gap of your material is will dictate the color that you see. So the emitted light, so the amount of light that is not absorbed will be the emitted light, and thus that's going to be the color that you experience, right? Or that your eyes experience anyway. Okay, so here's an example of light absorption in semiconductors. As I mentioned, the absorption of light in the semiconductors will vary with wavelength. So here is a list of semiconductors: germanium, silicon, indium phosphide, gallium arsenide, cadmium telluride, cadmium selenide, amorphous silicon, cadmium sulfide. These are industrially relevant semiconductors. They're used in homojunction photovoltaics, so that means you have one material in your solar cell, or heterojunctions to maximize the efficiency of your solar cell. So typically when you see all those arrays of silicon or of, the solar farms basically, right, that's basically, well, depending on what the cells look like, it could be amorphous silicon or crystalline silicon. But what you see here is the absorption coefficient. So how much of that incident photon is going to be absorbed. If we look here, here's the visible, right? It's 400 to about 700. So this is going to be the visible range of light. So that means if you have some semiconductor, let's say we take, germanium, or we take amorphous, here in black, amorphous, amorphous silicon. If we look at even a germanium, right? If you have a photon that comes in at 1,000 nanometers, that's in the infrared. That's in the infrared. Will most of that will that photon be absorbed? And the answer is no. Most of it won't be absorbed because the absorption coefficient decreases quite a bit by 2 orders of magnitude versus what's in the visible region right here. So let me draw a much better straight line. So in this region, it's highly absorptive. So if you have a wavelength that is longer, so the energy of that photon is lower, it's not likely to be absorbed. Okay. So what people have done is they can take a look at the band gap and say, okay, well, if I have silicon, its bulk band gap is 1.12 EV. Amorphous silicon, its band gap is a little bit higher due to, a number of things. It's actually quite controversial as to why the band gap of amorphous silicon is larger than that of crystalline silicon. But the takeaway is there's a push and pull between manufacturing and the cost, and also the efficiency. How much more efficiency can you get by just changing the crystal structure of your material? So we talked about in crystal structure of materials, and also defects, right? We talked about how if you want to make single crystal silicon, it's going to be it's a costly process, but it can be done, and it's obviously done in the you know, by Intel and other companies where they need that sort of thing. And so the Czochralski method, you know, it takes a long time. You get this huge ingot, and then you have to start slicing it. Now, let's say you just take a bunch of silicon, doesn't really matter. You can make it polycrystalline or amorphous, and the manufacturing, the processing to get amorphous silicon is much less costly, right? But if we look at the red here versus the black, so let's take a look at crystalline silicon and amorphous silicon. So in the visible region, you see here the absorption coefficient actually being higher, right, in black than that of this red region for the same wavelength, right? So this is a great example of how if you understand the crystal structure, then you can engineer better materials. And also if you understand the optical properties of material, you can also engineer better materials or higher performing materials. So when you decrease the processing costs, you know, it takes less to make amorphous silicon, you could see that the absorption coefficient is higher. So your decrease is down, but sorry, the absorption coefficient is up, and the manufacturing cost is down. Now, people have known this for, you know, since the 1970s, actually. Now, the other things you might want to consider is, well, why do people still make crystalline silicon, or why is it that you can still buy silicon, crystalline silicon? One of the reasons is the thermal conductivity, you know, the thermal, how your material handles heat. So on a really hot day in the desert, you know, how much does that heat affect the efficiency of a photovoltaic cell? You know, well, crystalline silicon can actually be slightly higher performing than that of amorphous silicon. So your efficiency actually goes down when you use amorphous silicon in really hot environments. So there is there is a push and pull there. So if you think about it, if you're in really extreme conditions in the middle of the desert and you have a huge solar array, you know, the thermal conditions could actually affect the decision as to whether or not you pay upfront higher manufacturing costs for crystalline silicon versus amorphous silicon, even though here the absorption coefficient for amorphous silicon is higher than that of crystalline silicon, right? So when it comes to materials engineering, you know, these are all the things one has to consider for manufacturing. So, all right, let's do another example where we look at computing the minimum wavelength values that can be absorbed. So the first example is a germanium. So the question is, what is the minimum wavelength absorbed by germanium if its band gap is 0.67 electron volts? Well, now we use the relationship between the wavelength of photons and the band gap energy. So here we're given the minimum wavelength that can be absorbed by germanium. We know what Planck's constant is. So basically we're rearranging. We're rearranging the relationship of energy equals hc over lambda, because we want to know what the minimum lambda is. So Planck's constant is just 6.63 times 10 to the negative 34 joule seconds. C is the speed of light, and germanium's band gap is 0.67 eV. That's been converted from joules to eV so that the energy terms cancel. And so you can see here that this is still in meters. And so the minimum wavelength that germanium can absorb is 1.86 times 10 to the negative 6 meters, which is 1.86 micrometers. So just remember to convert your units properly. If we want to ask, okay, well, what about silicon, which is less expensive than that of germanium? If we want to calculate that, we do the same calculation, and but silicon has a band gap of 1.1 eV in this case. And so if that's, we can do the same computation to get the minimum is actually 1.13 wavelength, so micrometer. So you can see here that the wavelength is less than that of germanium, right? And so here you need a higher photon energy, the shorter wavelength, you need higher photon energy to be absorbed by silicon. Now, this is for a perfect material, right? We're not talking about materials with impurities. If there are impurities, and we've seen this when we intentionally dope, let's say silicon to get N-type or P-type, then we can generate acceptor states closer to the valence band, donor states closer to the conduction band. And so then there, you can have the states within the band gap. And so then we can talk about that in a little bit when we talk about the laser. So let me stop here and look at some of the questions. And it says, for this problem, how to calculate the maximum wavelength absorbed by germanium or any material? Okay, well, you're not limited, right? You can always have higher energy. What what this example is telling you is, well, what's the minimum wavelength, right? What's the minimum photon energy that can be absorbed? So it has to be a wavelength that is equal to that of the band gap or higher. So can you have higher? Yes, absolutely. There is really no max, right? You can absolutely get higher. The only problem is once you, if your photon, there are other processes that can occur when your photon has higher energy than the band gap. You only need a minimum value, and that's the band gap energy, right? So let's say you have a photon that is 1.86 micrometers, it needs 0.67 eV, it will excite. Let's say you have energy that's higher than that. Well, what can happen? It will excite that electron, but then it can cause other dissipative processes, like it can heat up your material, things like that. So the energy can be absorbed in different ways besides just excitation of the electron going from valence band to conduction band. All right, so really there is no calculation for max wavelength because anything higher can be absorbed. So the sky's the limit, really, right? Gamma rays, all of that. So, okay, I hope that answers your question. All right, so we've gone and talked about a number of things: reflection, absorption. Now let's talk about transmission. So that's a relationship in which the fraction of light is not reflected or absorbed. That will be the amount that is transmitted. And so here you see a version of Beer's law, but it takes into account the reflectance. Oh, sorry, I thought there was, must have deleted the animation. So, and we know how to calculate R from our previous discussion of reflectivity. Now let's talk about colors of non-metals. What do you see? I should also say the color of metals, it's mostly like silverish, you know, well, not, it's mostly like a grayish hue, but of course, you know, with the examples of copper and gold, you can have some color, and that's the plasmon frequency that you're experiencing. But for the most part, you know, metals have this grayish tinge to them. For non-metals, the color is determined by the distribution of the wavelengths, right? So how much light is transmitted, and then the light that's re-emitted from the electron transitions, that's what you experience. So in the first example, cadmium sulfide, its band gap is 2.4 eV. So that means its band gap is much bigger than what we just talked about, you know, 0.67, for germanium, 1.1 for silicon, 2.4 is now in the regime of the visible range. As I mentioned, red was 1.6, violet is 3 eV, and so 2.4 is somewhere in between there. Okay. And so it will absorb higher energy visible light. And the color that you see, because it absorbs these different colors, the emitted color, the transmitted that you see is actually red, orange, or yellow. The second example is the example of ruby, in which you have sapphire. So this is not the gemstone sapphire that you often see colloquially referred to as sapphire. This is single crystalline Al2O3. Okay, so what that typically looks like is, let's see. Right, so what that typically looks like is here. So single crystalline Al2O3 is transparent, as you can see here. So here are the different examples in which it's cut into disc size for spectroscopy applications. And so when you have single crystalline Al2O3, that's sapphire, and you add in some impurity concentration, some dopant concentration up to 2 atomic % of chromia, Cr2O3, so aluminum is in the 3+ state, chromium is also in the 3+ oxidation state. What that does to your the band gap, or the color that you experience, is that it will change it from that transparent color to, or clear and transparent, to red. And how that happens is what I was talking about before, where you have octahedral coordinations. You have chromium, it's surrounded, by oxygen, right? It can split so this is a 3D transition metal. It can split your 3D, right? Before we talked about the 3D states having five states that are the same energy. It can split it into something that looks like this in an octahedral environment. And what you could have, and they just happen to be called T2G and EG, but that doesn't matter so much. You can basically have an occupancy, right, that looks something like this. Actually, 3, 2, yeah. That can look something like this, in which case, then when you excite, when the photons come in and you have relaxation, what's happening is you create these states. The chromium, you have these states where then the electrons of this energy or wavelength can come down, and the photons that get emitted have the energy of 560 ish nanometers, which corresponds to green. And because the absorbed wavelength is green, what you really see is red. Okay, so the resulting color, as it says here, is the reason why ruby is red, and it's purely because you have impurities of chromia in your aluminum. Right? So that's what gives it the red color. Otherwise, if you didn't have these impurities, if you had single crystal Al2O3, it would just be clear and transparent, because the band gap is much higher than 3 eV, right? Which is the end of the visible region, what our eyes can see. Okay, let me pause here and take a look at the question section.
Professor, the big question that sort of stuck to me that I'm not finding a quick answer for is regarding the plasma frequency and what happens when light of a greater frequency is shined on a given material.
Okay, so that just means then the material will be transparent to that frequency, or that wavelength, or that energy. So the example is X-rays. They're much higher energy and shorter wavelength, right? They're typically like 1.54 angstrom for copper, K alpha, or if you go to a synchrotron national facility, they can be like 0.2 angstrom. So they're much shorter than that of the plasma frequency that that were listed there, like 90 nanometers, things like that. Wavelength. Right. I use frequency and wavelength interchangeably because one, frequency is just c over lambda. So, it's just related by the speed of light. Well, inversely related by the speed of light. So if it's shorter than that, then your material will be transparent to that wavelength. So we use it to our advantage because we know, okay, if X-rays are going to go through a material, we can use the scattered X-ray, the scattering pattern, the diffraction pattern, and look and basically fingerprint what kind of material we have, like what crystal structure we have. So that's the short answer to what happens when the wavelength is shorter than that of the plasma frequency. Okay. So let's see, there's another question. If frequency is greater than plasma frequency, will that light have to be transparent? Yep, it will go through, it will be transparent. So it's gonna, that photon is gonna go straight through. Okay. All right, I think that's it for now. Okay, now let's talk about luminescence, or re-emission of light by a material. So if a material absorbs some light, and this question came up at the end of the last lecture after the 55-minute mark. When a material absorbs light at one frequency, right, or one wavelength or one energy, it can excite electrons from the valence band to the conduction band. When it re-emits it at another frequency, typically at a lower frequency, right? We can talk about, how does that happen? That means there are some trap states. There are some donor acceptor states in between the valence band and the conduction band. And so here you could see an excited electron going from the valence band to the conduction band. It can go into a trap state here. It can then be excited up here. It can go back to the conduction band, and then it can now re-emit, through some complicated process, go down to this other level. So all of this, if the electron is trapped in these states for a quote unquote long time. What is a long time? It's longer than 10 to the negative 8 seconds. So if it's longer than that, which of course seems really short, right? If it's longer than that, then we call that phosphorescence, right? So that's basically glow in the dark type material. If it's shorter, we call that process fluorescence. And that just is an indication that the occupation in these trap states are short based on our definition. So when we talk about photoluminescence, we're talking about systems where you can use photons, right, to illuminate, to cause some sort of optical property change. So here we can talk about, this example where if there's an arc between, that's created between two electrodes, they can excite electrons in, let's say, a mercury lamp, and then we'll get it to a higher energy level. When the electrons fall back to the ground states, right, as they do, because electrons at higher energy tend to go to lower energy, some wavelength, let's say UV, is then emitted. And of course, if we change, we can have different materials here, like phosphates. We can tune the color by just changing the chemistry that you see here. So we change the anion or the cations, calcium, with some substitutions, we can change the color. Let me come back to the, well, cathode luminescence. Let me come back to this, and just because the amount of time that we have, I want to cover the laser. So lasers are obviously important, but what's important about them is not just the fact that it takes into account the fact that you can excite, electrons from valence band to conduction band, but lasers do it in a coherent way. So the emitted light just don't go everywhere, right? They go in one particular direction in phase, and so that allows you to have a concentration of those photons. And so a laser is just an acronym for light amplification by stimulated emission radiation. So what does that actually mean? It just means that you have, when you excite the valence band, the electrons from valence bands to conduction band, in a laser, what you're really causing is population inversion, right? For the most part, when you have just a material, most of your electrons are going to be at a lower energy state. In lasers, they tend to be at a higher energy state. So let's talk about how that happens. What happens is, typically, let's say you have this ruby laser, our favorite material. It has some chromium in it. When you have a xenon lamp, that puts out wavelengths of 0.56 microns, that has a certain amount of energy. That is enough to excite electrons from the ground state to some excited state, right? But in ruby, as we've seen, there are some trap states, there are some metastable states. And so what happens is those electrons can relax to the metastable state, and and what you don't see is the emission, because that's non-radiative phonon emission. So your phonons are, your atoms are vibrating, but you don't see a light emission. If it gets stuck in this metastable state, at some point it will, relax down. In a typical laser, the number of electrons that are in the metastable state, so your population at a higher energy state, is greater than that of those in the ground state. So that's population inversion, right? The population of your electrons in a material that's not perturbed, that's in equilibrium, tend to be in the ground state, which is why we call it the ground state. But in a laser, you have the excitation from a xenon. For this ruby laser example, you have excitation from a xenon lamp that has incident photons of 0.56 microns. Those electrons go down to the metastable state, and at some point they will be emitted because they'll relax down to the ground state at some energy. I think it's like 6.8 or microns. So you experience it as red. Now the important part is, how do the emission of these photons or self-organize? Well, you can create a coherent emission by basically engineering your laser so that one side is highly reflective. So any of the emission that go this way will then be reflected back, and on this side it's semi reflective, and so it'll actually go out this way. Okay. And so you can have what's called pulse, where you have these cascading effect, or you can have a continuous type laser where you just have a continuous wave that, instead of a pulse beam, it just continuously excites all these electrons. But the important part is that in a laser, the emissions, they just don't go everywhere. They go in phase in a coherent manner. And that's all because of the design of the tube itself, right? That you have one side that's mirror polished so that you have reflection, and then they all go in phase and out the other side. Okay. So with that, it looks like we're nearing the end. So let me just take a look at the questions to see if there are more additional questions since the last time I stopped. And it looks like there isn't. So we'll adjourn class for today. All right, I'll see you next time, everybody.